Greetings, Earthlings. Today we're taking a look at the stupid computer. Now, that's actually the name of the computer. I mean, you probably have a computer and you say stupid computer all the time, but this one was actually called the stupid computer. So what is it? Well, this was a project for a college lab class, term project that I did around 40 years ago. When I was a young student at the Mars Institute of Technology. It's a 12-bit microprogrammed computer with a single accumulator. We'll see that shortly. And STUPID actually is an acronym. It stands for Simple 12-Bit Unadorned Programmed Instruction Decoder. It could be a useless programmed instruction. The U could stand for useless because, as we'll see, it doesn't have a whole lot of I/O. It's got terminal out, but no terminal in. Although, if you refer to the write-up, and I'll link to that later at the end, you'll see that I figured out a way that I could have added that. So this was built as a term project in a lab class. They gave us racks and these like plug-in modules. It's all TTL based, well, and some LSI circuitry, which is probably not TTL, but mostly small-scale, medium-scale integration. These were on little, well, not very little by today's standards. They were on plug-in cards, and you would plug them into the back of this panel, and then you would punch down wires on the front side to connect them together. So, as I said, this was microprogrammed. It's not a PDP-8. It's not anything you're familiar with. So let's take a look here at the block diagram. Down in the corner there, you can see the control logic, which runs the microcode and generates the control signals for the main circuitry, which is most of what you see on the screen right now. The biggest box there is the ALU, or arithmetic logic unit, that everything sort of revolves around. There's a single accumulator. There's a program counter. Up top here, there's a switch register. I call it a register. Switch register. That's just feeding front panel switches into the thing so that you can read the switches. Other registers, there's MAR and MWR, memory address register and memory write register, and then a memory buffer register, which wraps back around to the buses there, the A and the B bus, which then feed the inputs to the ALU. So every instruction that involves data, and that would include a jump where you're modifying the program counter, passes through the ALU. Now, due to the nature of that this was for a lab class, there's a limited amount of hardware. You have a limited amount of rack space you can use, and a limited set of chips or modules to choose from, and a limited number of some of those. The thing has some rather severe limitations. First of all, the biggest one is probably that we were only allowed one RAM card, one RAM module, and that was a 1K by 4 random access memory. This is a 12-bit machine, so I need it 12 bits wide. So what I can get out of that is 256 by 12 bits, and not in one read cycle. So there's some little extra state machines to handle the reading and the writing of the RAM, which we didn't see there in the block diagram because I thought it was pretty crummy that they made us do that. But hey, available rack space was another issue. We were supposed to do this in teams, and each person in the team was allocated one rack. I said, no, I want to do it on my own, but I'm going to need more than one rack. When I went in to present, you had to actually go in and present a proposal to the instructor and the teaching assistant, and then they would approve it or disapprove it or suggest some changes or whatever. So I said, this is what I want to do, and I want to do it solo, and they're like, well, that's like either an A or an F. And I'm like, I'll make it work. But I need 2 racks. And he says, instructor says, I'll give you the 2 racks, but, good luck. And then we'll also see there's some front panel kludges. The front panel is limited. I had to make use of what was there. So, normally you would have switches to examine memory and deposit data in memory and so on, run. start, continue, stop, reset, your typical front panel switches. Well, I didn't have all that available to me, so as we'll probably see later, if I decide to show it to you, I had to kind of work around that. The other thing is I'm limited in the number of registers I have, partly because these buses that are shown in the block diagram are actually implemented as multiplexers. So the A bus, I used a 4-input multiplexer. The B bus, I actually used a 2-input multiplexer, even though you see 3 inputs in the block diagram. So one of those inputs got tossed, and it was the TTY input, which is, I mentioned earlier, there was no TTY, no keyboard available. So you had to do all your inputting, even if you're running a program, through the front panel switches. So because of that limitation, I had to use a couple of memory locations as temporary storage. So locations 0 and FF hex are temporary locations, and that really just sucks. But as I said, I was dealing with these imposed limitations, and that's why they call it engineering, I guess. If I were to do this over today, I would eliminate all of those limitations. I would implement it with a full 4K of RAM. Wow, 4K, yeah, that's a lot. TTY input as well as output. Oh, wait, I should go back and mention, the microcode is 16 bits wide. I was allowed 2 ROM chips. They're 256 bytes per ROM chip. It's an old 1702 or something. So I have 256 micro instructions total to implement the whole thing. And I would eliminate that restriction today as well, and build a proper front panel for it as well. Okay, so let's take a look at the instruction set. Again, 12 bits, and it's a single word per instruction. There's no fancy, multi-word instructions like you see in a lot of processors today. Oh, and of course, being limited to 256 bytes of microcode, and including in the microcode a power-on self-test, it's a rather limited instruction set. The way the instructions are encoded, the high 4 bits, or the high nibble of the word, is the opcode, and then the remaining 8 bits can be an address in memory, or they can be further decoded, which you'll see in the F instructions down at the bottom. So 0 is hauled, 0 anything, 0XX would be hauled. Rather wasteful of instruction space, but again, microcode limitations, and the PDP-1 was wasteful of not all possible instructions were used. So obviously you could do a lot more with this. If you had more microcode space, you could add certainly more instructions. Add, subtract, and an or, clear a memory location, increment and skip of 0, decrement and skip of 0, load the accumulator, store the accumulator, hang the processor. That's a fun one. Well, I just needed it to do something. There's a branch, or a go-to, or a jump, whatever you want to call it. I called it branch because it's opcode B, and then it's branch if 0, branch if negative, branch if positive. Okay, then a whole bunch of no-op instructions, only, one of which I would actually keep if I expanded the instruction set. I defined a get-care operation, but because of the limitation of just the 2 inputs on the B bus, that didn't get implemented. There's a put character, and there's a read switch register, and that's it. That's the whole instruction. There's no multiply. There's no divide. There's no exclusive or, and there's no carry bit either, I might mention. So there's no branch on carry. There's no testing for things like overflow and things like that. Okay, so let's take a look now at the microcode instructions. There are 3 types of instructions here. There's the ALUs, which have the high order bit set to 1. There's branch instructions. Now this is, again, a microcode branch, and it's branch on a condition, always, with 8 bits of target address. And there's what I called an operation, which would be like, obviously it's not an ALU. It's everything else. It's just throw all the leftovers into there. Reading and writing memory, dispatching on the opcode, turning on the lights and things like that. And that's the microcode instruction set. ALU, specifies a source and target register. Notice I did allow 2 bits for the B input, but again, I only implemented that as a 2-input multiplexer because that's what they would let me have. So I guess only bit 3 is used. There's a carry in. Now I said there's no carry bit, there's no carry register. But on the ALU, there's a carry in bit. And so if you want to increment a value, you're setting that carry in bit. The ALU is implemented with 74181 chips, which I don't think you can get anymore. Well, you can't get them new. I don't think they make them anymore. You could find them on the surplus market if you were to foolishly want to try to recreate this thing. Okay, the function bits specify, they just go straight to the ALU, and they specify what operation you want to perform. And the destination, which is a single bit per destination, so you could actually send the result to 2 places at once, although I don't think I ever do. Okay, that's the microcode. Let's look at the backplane layout, or the rack layout. You can see here there are 3 rails. Now each rack actually only had 2 rails, so that one down at the bottom is that overflow stuff, which I knew I was going to need for the second rack. So the top 2 are 1 rack, and the bottom 1 rail there is a second rack. And you can see how it's laid out here. And in most cases, they're called MSI and then a number. If you replace the MSI with 74, that's what it had on it, although it might have more than one of them. There's an LSI. Well, the memory is an LSI 2102. That's the 1K by 4 memory. And I think there was some small scale. Well, the small scale integration are the 500 series there, I think. I see 574, which would be most likely 7474s. There might have been more than one of them. 500 was probably NAND gates, 7400s. Yeah. And then LSI 1702s. We'll go jumping back up to the top. Look in D and E on the top rail there. LSI 1702, those are the ROMs, which were EPROMs, which hold the microcode. So pretty much A through I there is the microcontroller. And the rest of it is the guts of the actual computer. Okay, so this gives you an idea of how many chips were involved. If it's 1 chip per slot, then, what have we got? This is like 22 per, so it's 50 some odd chips, or thereabouts. Now the front panel looked like this. And unfortunately, it did have 12 switches, but you can see they're broken up into a series of 8 and a series of 4, which is really kind of annoying, but I had to make do with that. There's the big toggle switches up at the top, and I had one of those I called magic mode, which I'll explain. The just round circles are LEDs, and it looks like I didn't even use all of them, and then there were a couple of 7-segment displays. So I was displaying the program counter in hex and the microcode program counter in hex. The accumulator value is in that top row there, all 12. They nicely gave us 12 lights there. And the micro instruction is over here to the right of the micro program counter in 2 rows of 8 bits. And then on the left, the circles with dots in them are push buttons. So there's a reset and there's a start. Notice there's no examine, there's no stop. Okay, so to examine and deposit and so on, that's what magic mode is for. What happens if you're in magic mode and you press reset is it will read the switches, the switch register, and it will display the value in that location, I guess on the accumulator lights. It's been a while, but I think it was on the accumulator lights. It would display the current value. You could then modify that location by setting the switches and pressing one of the buttons. I'm guessing it's start. And probably it would increment the program counter or whatever register it was using to access the memory, maybe just the memory address register, and display the next location. And so that's how you would enter a program. Once you got it all entered, then you would flip the magic mode switch off and hit reset again, and then it would come up in normal mode. Yes, if you were to do this today, well, maybe you wouldn't show the microcode, the micro instructions, the micro PC. But you'd have a proper row of 12 switches for data switches. You'd have proper lights showing the accumulator and the program counter, and maybe other things as well, memory address register, who knows. And then you'd have switches for deposit, examine, deposit next, examine next, things like that. And get rid of that magic mode, because it's just a kludge. So that's the overview. If you want to look at the actual details of the implementation, the actual low-level hardware design, and the microcode, it's all there on the hackaday.io site, full schematics and everything.